This is Chapter 8, Gases, and Section 8.3 is the relationship between temperature and volume. This is Charles's law. Charles's law states that the Kelvin temperature of a gas is directly related to its volume. This means that the quotient V over T is constant as long as you hold P and N constant. Okay? P is the pressure, N is the number of moles. So what that means is if you double the temperature, the Kelvin temperature from say 200 to 400, the volume will have to double as well, as long as P and N are being held constant. So if temperature increases, volume increases. You can also think about it in the reverse way, that if the volume increases, the temperature will have to increase in order to maintain the same pressure and number of moles. So this can be expressed in this mathematical relationship, V1 divided by T1 equals V2 divided by T2. And this is the mathematical expression of Charles's law. Just like with Boyle's law, Charles's law is often seen as the relationship between the properties of a gas before and after some change. So you have the initial volume and temperature, V1 and T1, and then one of those variables is changed, and then the other one will change as a result to adapt to the new situation. So that means that there's generally two types of problems that you get with this. One where you need to find the new volume, and one where you need to find the new temperature. Okay? So we have these two examples given here, and we just want to look at the algebra to do that really quickly so that we can be comfortable with it. So the first one is the easiest. If you're given the initial volume and temperature, and you're given the final temperature and asked to find the final volume, then you're just solving for V2. And that's very simple. To get V2 by itself, you just have to get rid of this T2. So to do that, you would multiply by T2 on both sides. That's going to cancel this out. And so you'll be left with V2 equals T2 times V1 over T1. And often this is grouped together, so you have V1 times T2 over T1. So the only thing I've done here is flip around the T2 and the V1, so this way we have the temperatures grouped together. Again, this is to remind you to cancel out the Kelvin unit. The second one is a little bit more challenging because we want to get T2 by itself, but T2 is here in the denominator on the right-hand side. So this means that we really need to cross multiply. We have to take T2 up here, and then take all of the variables on the left-hand side and bring them over to the right, so that T2 will be by itself. So that means taking V1 down here and taking T1 up here. So when all is said and done, you get T2 by itself, and that equals V2, which was already on the right-hand side. This T1 has come up next to V2, so T1 is here, and this is going to be divided by V1. Okay? And so again, we can sort of recast this equation as T1 multiplied by the ratio of V2 to V1. Okay? And this allows you to see that you're canceling out the volume units this time in favor of the temperature unit. Let's take a look at an example of where we would need to use Charles's law to solve a problem. This problem says a balloon has a volume of 785 milliliters at 21 degrees Celsius. If the temperature drops to 0 degrees Celsius, what is the new volume of the balloon at constant pressure and moles? Okay? So when you're reading through like this, again, it's useful to just sort of mark up the question with information that you'll need from it, right? So underline everything that looks important. So this first thing that I've underlined is 785 milliliters. That is clearly a volume. This next thing is clearly a temperature. Okay? At this point in the question, we're not sure whether it's changing or what's going on, so we'll just leave them as V and T for now. Then the next sentence says, if the temperature drops to 0 degrees Celsius, so what we have here is a new temperature, right? So now we can start to think about what kind of equation we want to use. This is a new temperature, so we'll call it T2, which makes this T1, and then it's asking for the new volume, which would obviously be V2, and so this must be V1. Okay? And then it reminds you again at the end that pressure and moles are being held constant. That means when we analyze this problem, it should be clear that we're given the relationship between volume and temperature, and the temperature is changing, and we're trying to see how the volume changes as a result. And so we need to use Charles's law to do this. Okay? And we can also predict at this point that since the temperature is decreasing, right, it's going from 21 degrees Celsius to 0 degrees Celsius, we're cooling this gas down, so we would expect that the volume would also decrease. Okay? And then the other thing we should always do immediately when we are presented with the gas problem is convert any temperatures that we see into Kelvin. Okay, so you take the temperature and you add 273, and you get the temperature in Kelvin. So you want to do that for all of your temperatures. Okay, that should always be one of the first things that you do. The next step then is to just rearrange, in this case, Charles's law to solve for the unknown quantity. Okay, this is similar to what we did before. We already saw the algebra for this, so we know that we get this expression at the end. But again, just to go through it again, to get V2 by itself, you have to get rid of the T2, which means multiplying both sides by T2, which brings it over here, and so you get T2 up here. Okay, so V2 equals V1 times T2 divided by T1. Once we have the expression for V2, all that's left is to enter in the values that we need. So V1 is 785 milliliters, directly from the problem. T1 is 21 degrees Celsius, but we converted that to Kelvin. We got 294. And T2 is now a lower temperature, 0 degrees Celsius. And when you add 273, obviously you get 273 K. And so the Kelvin units in the temperature cancels out, which will leave us a milliliter unit, since that's what this volume is given in. So you multiply all these together and you get 729 milliliters. And that's your answer. Here's another example where you need to use Charles's law, but this time you want to find the new temperature rather than the new volume. So the question says a sample of oxygen gas has a volume of 420 milliliters at a temperature of 18 degrees Celsius. At what temperature in degrees Celsius will the volume of the oxygen be 640 milliliters, as long as P and N are held constant? Okay. So it's asking us for the new temperature, right? At what temperature will the volume be 640 milliliters? So this would be the new volume. The original volume was 420 milliliters, and the original temperature was 18 degrees Celsius. Again, analyzing this problem, the first thing we should do is put the temperatures that were given into Celsius. So 18 degrees plus 273 is 291 K. Okay. V1 is given to us as 420 milliliters, and V2 is 640 milliliters. And so we need to find T2, which means Charles's law. Okay. And again, we can predict the volume is increasing. It's going from 420 to 640, and so we would expect that the temperature is increasing as well, the Kelvin temperature. The next thing you need to do then is to rearrange Charles's law to solve for the unknown, which in this case is T2. We already saw this algebra, but just to emphasize it and to give you a refresher on it, we're going to go through it again. Now, before we said that we just cross multiply, but cross multiplication is really a shortcut for the kind of algebra you need to solve this. So to get T2 on its own, we see that T2 is in the denominator here. So we need to bring T2 into the numerator so we can multiply both sides by T2, which will cancel it out on the right-hand side and put it into the numerator on the left-hand side. Okay? But then we need to get rid of these variables on the left-hand side to get T2 by itself. So to get rid of these variables, you multiply by the reciprocal. So it'll be times T1 over V1. Okay? That way T1 cancels out and V1 cancels out. And so then we have to do the same thing on the other side, multiply by T1 divided by V1. And so finally T2 will be on its own on the left-hand side, and this is going to equal V2 on the right times T1 divided by V1. Okay? And again, we can group these together so that the volumes are together, and so this will be T1 times the ratio of V2 to V1. And this again helps you to remember that you want to cancel your volume units, that your volumes really need to be in the same units. Step 3 then is once you have the expression, you just fill in the variables. So the initial temperature, 18 degrees Celsius, is converted to 291 K here. The initial volume, V1, is 420 milliliters. The new volume is 640 milliliters. Since the new volume is larger, this factor is greater than 1. And so when we multiply the temperature by a number greater than 1, the temperature will go up. Okay? So in this case, the temperature goes up to 443 K. Just remember that the question is asking for Celsius temperature. So in order to go from Kelvin to Celsius, we have to subtract 273. So 443 minus 273 is 170 degrees Celsius, which is B. Now let's use the gas laws to complete each of these sentences with either the word increases or decreases. So pressure blank when volume decreases at constant temperature and moles. So this is the relationship between pressure and volume. So this is from Boyle's law. And we know that pressure and volume are inversely related. So when volume decreases, the pressure is going to increase. When T decreases, V blank at constant pressure and moles. Okay? And so this is the relationship between V and T, which we're learning here. It's Charles's law. So T decreases, that means the volume is also going to decrease because these are directly related. Okay? Cooling a gas down tends to decrease its volume. The next one, pressure blank, when V changes from 12 liters to 24 liters at constant temperature in moles. So this is like the first one. We're going back to Boyle's law, but now the volume is changing by going from 12 to 24. That means it's increasing. So that means that the pressure will be decreasing. And then the last one, volume blank, when T changes from 15 to 45 degrees Celsius at constant pressure in moles. Again, Charles's law, temperature is increasing, volume is going to increase as well, because they're directly related.